Hello, BC Calculus students. This is Mr. Johnson, and this is section 4.3, which is on the mean value theorem, and also the other derivative tests and the behavior of the first and second derivatives on the function f of x. So let's start with the mean value theorem, which is one of our main, very important theorems as we work our way through calculus. Remember, we have the intermediate value theorem, the mean value theorem, the extreme value theorem, or it's also called the min-max existence theorem, and the fundamental theorem of calculus. With the mean value theorem, we have a function f that is differentiable, and if a function is differentiable, then it is automatically continuous, so it implies continuity, and it's continuous on the interval a to b, which is closed, but it's differentiable on the open interval a to b. That doesn't really say it very well in that first statement there, but if you look down just a little bit further on the page, it does say it really well right here, is that again, it has to be continuous on the closed interval a to b, but differentiable on the open interval a to b. So the theorem says that there exists a number c that is in between a and b, such that f prime of c is equal to f of b minus f of a divided by b minus a. And what this really means is that the average rate of change, which is written right here, is equal to the instantaneous rate of change, which is the derivative. So that is our mean value theorem. So the instantaneous rate of change is equal to the average rate of change for some value on the interval as long as f is differentiable. You may also see this written as f prime of c multiplied by b minus a equal to f of b minus f of a. So what does this actually look like on a graph? So let's say that you have some sort of function f of x that looks maybe like this. And let's say that we have 2 points on this graph. Let's make this B, and we'll make this one A. And if we connect the 2 points, we form a secant line. And the slope of the secant line is equal to the average rate of change over the interval from A to B. So we have f of b minus f of a divided by b minus a. So that's the slope of that secant line that's formed between those 2 points. So the theorem says that if we have a differentiable function, which I did draw here, then at some point on the interval a to b, there is a tangent line that is parallel to the secant line between a and b. So we have a point right here, roughly, that is c, and that is the slope of the tangent line, which is equal to f prime of c. So that's the visual behind what's happening. Now, there may be multiple values of c along that interval for which the instantaneous rate of change is equal to the average rate of change, but the theorem says that it's guaranteed that it will happen at least one time. Okay, let's move into example 1 and take a look at this at least just a couple different ways with these first couple examples. We're going to look at this cubic function g of x, and we're going to look at the interval from -1 to 1. And we're looking for a value c such that the average rate of change on g of x is equal to instantaneous rate of change at c. So the first thing we're going to do is find the average rate of change, or the slope of the secant line, which is f of 1 minus f of -1 divided by 1 minus a -1. And we get f of 1, which is 8, minus f of -1 is 0 over 2. So we end up getting 4 for the average rate of change. Now let's go ahead and calculate the derivative of g. So g prime is our power rule, 3 times x plus 1 to the second. And we're going to then set up our mean value theorem equation. So we have g prime of c, which is equal to 4. So some value c on the interval a to b for which the average rate of change is equal to the instantaneous rate of change. And we're just going to simply solve this. So we have 3 times the quantity c plus 1 squared equal to 4. And that gives us c plus 1 squared equal to 4/3. We could take the square root of both sides, which causes us to get the absolute value of c plus 1, which we could change into plus or minus the square root of 2 over 3, 2 over square root 3. And you notice that when we solve for c here, we actually get two different answers. And the reason is that if we were to move outside of the interval from -1 to 1, there's actually two spots in this particular graph for which the instantaneous rate of change is the same as the average rate of change. On the interval -1 to 1, however, the only value of c that does work is this positive value, which is -1 plus 2 over root 3. Okay, I just inputted a graph that I think is going to hopefully help. So this red graph here is g of x, and the blue one is going to be your secant line between -1 and 1. So this is the secant line here, this blue one. Okay, so when we look at what we just found, we figured out that at this value c, which let's say that c is about right here, that value c, there is a tangent line that is parallel to that particular secant line. Now you'll notice if we were to extend this interval a little bit further and we were to go from -3 area here to 1, you can see that there actually is a second spot for which a tangent line would be parallel to the secant line. We didn't include that because that didn't fit into our particular interval, but that's why we ended up getting algebraically. We got those two different answers, but just the one answer, -1 plus 2 over root 3, that's the only one that ends up working in this particular interval. And so we should be aware of the fact that we may get multiple algebraic answers, but they might not all work in the particular interval that we're given. Okay, let's go ahead and move on to example 2. So with example 2, we're going to try to find a c on the interval of 0 to 4, such that c is equal to the average rate of change of f of x on the interval from 0 to 4. I'm going to graph this one because I think it's going to help us a little bit. So here we have a vertical asymptote at 3. So that's a vertical at x is equal to 3. We also have a horizontal asymptote at the x-axis, so y equals 0. And when we graph this function, it looks something like this. And if you notice, if x is 0, so I'm just going to substitute in x is 0, I get -1/3, which is this point right here. And then if I substitute in 4, I get 1 divided by 1. So I get 1, and that's going to be approximately there. This isn't really totally to scale, but either way, if you were to connect these two, you can see that this secant line, I suppose, between these 2 points goes over this vertical asymptote. In other words, the function f of x is not continuous on this particular interval from 0 to 4. And because of that, the mean value theorem does not apply. So I'm just going to pause and write out that statement. All right, with this problem, it might have been a little bit more obvious because we kind of know this graph, but sometimes AP can be a little confusing and a little tricky when they try to ask this. So you just have to be very aware that you don't get caught up in a problem and apply the mean value theorem and come to find that the function itself is not continuous. So, first check, is the function continuous? Second check, is it differentiable? And then you're able to apply the mean value theorem. But in this case, we're unable to apply it. Okay, let's go on to the next page. Okay, on this page, we're going to look at example 3, and we're looking at the function f of x equal to the third root of x. And this graph looks something like this. It's kind of an interesting graph because there's a portion of it, and I'm kind of exaggerating this, but there's a portion of it that actually becomes vertical. It's a continuous graph. So in other words, you could put any value in for x and you'd be fine. You can take the third root of any value in the real number system. And so this graph is continuous. However, there's a portion of it for which there's a vertical tangent, and that is an issue for us. I'm going to show you just algebraically what I'm talking about. So if we take the derivative of this, we get 1/3 x to the -2/3. And if you were to calculate f of 0 here, maybe I'll write it like this: 1 divided by 3 times x to the 2/3. If you were to take the derivative at 0, you would have 1 divided by 0, which is clearly undefined. And so because of that, the derivative does not exist at a certain value of f, making f not differentiable at the value of x is equal to 0. So when we're looking at the interval -3 to 3, f is not differentiable over that whole interval, even though it is continuous. And since it's not differentiable over the entire interval, then we cannot apply the mean value theorem. So I'm going to pause again and I'll write out that statement. Okay, what we're going to do with example 4 is take the exact same problem, except we're going to restrict the interval to go from 0 to 1. Now remember, the function f of x is not differentiable at 0, but if you recall from the previous page, the mean value theorem says that f of x has to be continuous on the closed interval, which it is. So f of x is continuous on the closed interval, but it has to be differentiable on the open interval, which it is. So just because it's not differentiable at 0 doesn't mean that we can just skip the mean value theorem in this problem. We can apply the mean value theorem on example 4 because of the full definition of the mean value theorem. So the first thing we're going to do is look at the average rate of change. And that's going to be f of 1 minus f of 0 divided by 1 minus 0. And that gives us a rate of change of 1. Then we're going to take the derivative. Now remember, we just did the derivative in example 3. So we have f prime of c, which is going to be equal to 1 divided by 3 times c to the 2/3 power. And we're going to set these two equal and solve. So we have 1 equal to 1 over 3c to the power of 2/3. And then I would just maybe multiply by c to the 2/3 and get 1/3. And c would be, now be careful here because when you do the 2/3 power, that's being squared. So when you're taking the square root of that and the third power of that to move it over, so you're taking the 1/3 to the power of 3/2, you do get a positive or a negative out of it, similar to kind of how we did that last, the example 1. But in this case, on our particular interval, we only get the one value. So we're going to get c equal to 1 over 3 to the 3/2 power, and we could write that as 1 over 3 root 3, or we could rationalize it, doesn't really matter, but there you go, that's going to be your c value, where the mean value theorem guarantees a instantaneous rate of change equal to the average rate of change. Okay, let's go ahead and take a look at example 5. This is, you can see from the answers, this is obviously a calculator problem. And so we're looking at the function f of x, and we're looking for the value of c for which the instantaneous rate of change of f at c is the same as the average rate of change over the interval 1 to 4. So this is just asking for the mean value theorem without calling it the mean value theorem. And so we're going to take a look at the average rate of change, which I'm going to go ahead and do by hand. You can certainly do this with a calculator as well. We're looking at f of 4 minus f of 1 divided by 4 minus 1. That gives us 4 plus ln of 4 minus quantity 1 plus ln of 1. And then we're going to divide by 3. So here we get 3 plus ln of 4 over 3. And again, you could do that in the calculator, but I just wanted to show you the development of it. And then the instantaneous rate of change, we'll have the derivative, which is 1 plus 1 over x. And of course, we're going to look at that at the letter c. Now, we're kind of stuck here. We're not going to be able to take and solve this equation by hand. But if we were to take our calculator and substitute both of these in for, let's just make this y1 and then y2 on the calculator, you can graph these two. You can use the answers to help kind of shape your window of this graph. We know the answers are, at a minimum about 0.4. We know the maximum is about 2.5. So you could take and kind of shape your window, but you want to graph both of these functions, and then you want to look at where they intersect on the graph. They're going to intersect at one spot. I've already done this on my calculator, and so I get c equal to 2.164. And remember, the c is just the x value. It's just the dummy variable there. So you're looking for the x value of the intersection, and that's going to be the letter C on this problem. Okay, let's move on to the next page. Okay, this is a really interesting problem because you might have remembered this from last year in AB. This is one of the worst problems, the worst one I've ever seen. There could have been, I suppose, a problem that was even lower average than this, but this is the worst problem I've ever seen on the exam regarding the average. The average nationwide was 0.96 out of 9 on this FRQ, which is really hard to even believe. But this is problem number 3 in the 2007 exam, and this is just part A and B. Part C and D weren't necessarily, I think one of them was a fundamental theorem and the other one was the derivative of an inverse. But part A and B tackles the intermediate value theorem and the mean value theorem. And in this problem, you have f prime, you have g and g prime, as well as a function h. Later on in the problem, I think in part C or D, they introduce another function. And so this problem had so many different elements to it. I think that students got really confused and had a hard time picking up any of the points. And that's why the average nationwide was so low. So we're gonna take a look at part A and B, which, like I said, are two of our important theorems throughout the year. So we have all the information in that table. We have the information in the text. We do know that G and F are differentiable, and we know that H of X is made up of G of F of X and then minus 6. So in part A, it says explain why there must be a value R in between 1 and 3 such that H of R is equal to -5. And if you have taken a look at enough problems, you know that this is the intermediate value theorem because we're looking at an interval and we're looking at trying to compare a function's value to that interval. And we know that if we can somehow prove that h is below -5 and h is above -5 on that interval, well then h must cross -5 as a value of y. So we're going to look first at h of 1. And we're going to use the definition of h in the text. So we have h of 1 equal to f of g of 1 minus 6. And we got to go up to the table. So we're going to take a look at g of 1, which is 2. So we have f of 2 minus 6. And f of 2 is 9. So 9 minus 6, and we get 3. So h of 1 is 3. Then we're going to do h of 3. So the other end of the interval, f of g of 3 minus 6. And then we have the same kind of thing here. We have, let's see, I'll erase those two. So we have g of 3, which is 4. F of 4 is -1. And so we end up getting -7 here. All right, so now there are many ways to write out the intermediate value theorem. One of the important things, one of the main things you need to include is that the function is continuous. If you think about the intermediate value theorem, if we prove that some value is here and some value is here, and let's say that we want to connect these and we want to cross a value in between these 2 points. Well, we have to state that the function is continuous in order to do that, because if we're trying to go from one point to another and all of a sudden we go like this and the function is discontinuous, well, then we just skipped this whole section in between those points. So one of the keys to intermediate value theorem is that the function is continuous. So we must state that. We also must state some relationship between the values that we found here, 3 and -5, or excuse me, 3 and -7, and how -5 is between those. We have to make a statement about that. You can use inequalities. You can try to compare them individually. But again, you have to somehow show that -5 is between those values. So what I'm going to do is I'm going to pause and write out one of many different phrases or sentences that would explain what the intermediate value theorem is telling us here. And then we can just talk about that. All right, so here is one possible explanation for part A. And again, it's a little bit wordy and you can word this in different ways, but it does highlight the continuity piece, as well as I just use an inequality to outline the different values we found comparative to the value of -5. So you just want to state the continuity, state the comparison, state the intermediate value theorem. Okay, let's move on to part B. So with part B, we have a very similar phrase. However, this time instead of talking about the function h of r, you're talking about that function h prime, and they're using c as just a different dummy variable. So why is there a value c for which h prime of c is equal to -5? Well, we're going to look at the instantaneous rate of change equal to the average rate of change. So I'm going to pause and write this one out, and then I'll talk about it. Okay, so with this one, we're stating that h is differentiable because both f and g are differentiable. With the mean value theorem, that is definitely one of the keys that you have to include is differentiability. Just because f and g are differentiable, we would want to be safe and say that because h is made up of them, it is also differentiable. And then we're looking at the average rate of change, and the average rate of change is here with h of 3 minus h of 1 divided by 3 minus 1, and that is equal to -5 algebraically. And so the mean value theorem would guarantee that there is a value in between 1 and 3 such that h prime of c is equal to -5. So again, you can see why just by looking at parts A and B, this problem was so difficult for everyone in the nation. But that's a nice outline of intermediate value theorem as well as mean value theorem. Okay, let's talk about a little bit of the behavior between the derivative of f and the second derivative of f, and then what they tell you about a function. And we've already talked a little bit about this in the last section. We're just going to outline this a little bit in a little bit more detail and kind of organize all the different aspects of this. So if you have a function that is strictly monotonic, it means that it either increases continuously or decreases continuously. And if it increases throughout, then f prime is positive throughout, and if it decreases, then f prime is negative. If you're looking at an inverse function, for example, so you're looking at wanting to create an inverse function, you have a guarantee that a function has an inverse over the entire domain if it's monotonic. Because if you have a function that always increases, its inverse then would exist for all values, and if the function always decreases, you would have an inverse that would exist. With concavity, our textbook talks about this as the concavity test. We've just always discussed how if f is concave up, the second derivative is positive, and if f is concave down, then the second derivative is negative. But again, the text calls that the concavity test. Let's move on to the next page. Okay, on this page, we're looking at just piggybacking off of the concavity tests, the points of inflection. So the points of inflection are when the concavity changes. So if a function changes from concave up to concave down, you have a point of inflection there. The candidates for that, so if you're trying to test points of inflection, you're looking for when the second derivative is 0 or undefined, and then you want to make sure to test that the second derivative does in fact change signs. We've talked about the local or relative minimums and maximums a lot, especially in the last section. But just to review a little bit, a local maximum occurs when a function is larger than another function in a small interval around that value. Remember the first derivative there will change from positive to negative at a local maximum. At a local minimum, the opposite is true. The first derivative will change from negative to positive. What I just outlined there was is formally called the first derivative test. If you're ever wanting to make sure that you understand whether or not you're looking at the signs correctly, I think it's always helpful to make a sketch. So let's say that we have a sketch of a simple parabola here where we have a local maximum. So with a local maximum, what's happening as we approach that value from the left side? Well, the function is going to be increasing. And what does that tell you about the first derivative? First derivative is going to be greater than 0. After that local maximum, we're going to be decreasing, and so then that first derivative is less than 0. You can always sketch either the function or the derivative to kind of get a sense of what's happening, whether it's a local max or a local min, or for that matter, you can look at concavity as well. So with a local minimum, maybe we have a parabola that looks something like this, and then you can do the same thing. You can look at that minimum, and you know that the function is decreasing to that minimum. That means the first derivative is less than 0, and then it's going to be increasing after, so that first derivative is greater than 0. So that's the sign change that we're looking for when it comes to local minimums and maximums. Now, one thing that we talk about in terms of the change of signs is that if f prime does not change sign, so if it has a critical point, let's say that f prime of 2 is equal to 0, it has a critical point, but there is not a sign change, then there is no local max or min. One of the problems that it might help us understand this is that you have maybe like the graph of y equals x cubed, okay? So this graph is increasing throughout. However, at the origin right here, you have a horizontal tangent, and so the derivative y prime equal to 3 x squared at x is 0 is 0, and so therefore you have a critical point there. You have a derivative that's 0. However, there is no local max or local min there because on the left side of that, it's increasing, which means that the first derivative is greater than 0, and then off to the right side, it's still increasing, and the first derivative is greater than 0. So there's no sign change, and we have to be aware of that on a problem where maybe we couldn't see it well. Maybe it's a set of points on a table or something like that. We want to make sure that we're cautious about making a conclusion when we do see that a first derivative is 0. That doesn't guarantee that we have a minimum or a maximum. So the first derivative test is pretty common on the AB exam. We use it on all sorts of different problems in different contexts. The second derivative test is not as common. And we taught you all this in AB last year. We didn't use it a whole lot because it doesn't come up as often. In BC, it does come up more often. It's still relatively rare, but it does come up a little bit more often. And so I want to try to explain what this is. And the statements that are written here are a little bit, some stuff is actually left out, and so I want to clarify. So let's first look at a function that has a minimum. Let's just take that parabola we were talking about. So here's a simple parabola with a relative minimum. Now, the one thing that's left out of these statements is that we must know that this is a critical point. So for both of these, we have to know that the derivative at this value c is equal to 0. If that's not the case, we cannot prove the second derivative test whether it's a min or a max. Okay, so there are some contexts where we know the derivative is 0, but it's really difficult or nearly impossible to tell what the sign change is. And we will see that in our next chapter, in chapter 8, when we do series and sequences. We'll have situations where we know the derivative is 0, but we aren't able to easily, or it's maybe not even possible to test the sign change of the derivative at that value. So instead of being able to do the first derivative test, which is to do the sign change of f prime, we actually go to the next level and we look at f double prime. So if f double prime is positive, that means that f is concave up. And if f is concave up and f prime is equal to 0, then f has a minimum. And then the opposite is true. If we have a situation where there's a critical point and f double prime is negative, and again f prime is 0, then f has a maximum at that point. So that's the second derivative test. It happens to be pretty helpful depending on the context of the problem. Okay, let's move on to the next page. All right, we're going to put everything together on this problem and try to just organize all the items that we just reviewed on the last couple pages. So we have this relatively simple function. We have part A, which is going to ask for the intervals for which f is increasing and the intervals for which f is decreasing. So we're going to first take a look at the derivative of f, which is 4x cubed minus 12x to the first. And we're going to look for the derivative to be either 0 or undefined. This is a parabola or a polynomial, and so it's always defined, which means we're just focused on the derivative equal to 0. So we have 4x times the quantity x squared minus 3, which means that x could be 0 or x could be positive or negative root 3. So these are called critical points of the function f. We're going to test these points on a number line, and we're testing the first derivative because we want to know when is the first derivative positive and when is the first derivative negative. One little trick that I often show people is that you can substitute in values into the function f prime and get a sense of whether it's positive or negative. So we could substitute in, let's say, 5 and plug it in, positive or negative. Okay, we know this interval. We could substitute in 1, plug it in, know this interval, and a negative 1, plug it in, know the interval, plug in 1, and so on. You could do that with any of your intervals. Another way that might be I don't know, a little bit easier is that if you look at the function f prime, it's a cubic function, and we know the behavior of a cubic function is like this. And so we just found the x-intercepts of that particular function. Specifically, this f prime would go like this through negative root 3. It would come down through 0, and then it will go back up through positive root 3. And we just found the sign is negative on the interval negative infinity to negative 3 because it's below the x-axis, positive, negative, positive. It happens to be really fast. It doesn't work every time because some functions are really hard to sketch, but if you can sketch a function, it's actually much easier than trying to plug in a numeric value to the equation. Okay, let's go ahead and just list out what we found here. So again, we're trying to figure out when f is increasing. So f of x is increasing on two different intervals. We have from negative root 3 to 0, and we have root 3 to infinity. And again, that's because that first derivative is positive. So then we have the intervals at which it's decreasing, and that's going to be from negative infinity to negative root 3, and then again from 0 to positive root 3. All right, that should do it for part A. Let's try part B. So part B, we want to look at the local minimum and maximum values of f of x. I'm going to write that over here actually. Well, this is pretty easy now that we have our information about when f is increasing and decreasing because we can use the first derivative test. So remember, when the derivative changes from positive to negative, there's a maximum, and from negative to positive, there's a minimum. So we have, let's do the minimum. There's two of them. It will be x is equal to either positive or negative root 3, because we can see again here on our sign chart, we can see the sign change to produce the minimum. And then for the maximum, we just have one value. It's going to be when x is 0 because there's a sign change from positive to negative. All right, let's move on to part C. So with part C, we're looking at the intervals of concavity and the inflection points. So we want the second derivative. It's going to be 12x squared minus 12. And we want to set it equal to 0. Remember, we also want to pay attention to any undefined second derivatives, but it's a polynomial, and so we're okay here. We can factor out a 12 and get x squared minus 1, and we can factor it one more time, get x minus 1 and x plus 1. Okay, so we have two critical points here, positive or negative 1. And we're going to do a sign chart again. This time we're going to use the second derivative. We just have 2 points to consider, negative 1 and 1. Remember, you can do the same thing. In this function, we have a parabola. It opens up, and so our second derivative might look something like this. And that means that we have a positive and a negative and a positive. And the question asks for the intervals of concavity. So we have f is concave up from negative infinity to negative 1, and then again from 1 to infinity, and then f is concave down from negative 1 to 1. Now remember, a point of inflection is going to occur when the second derivative changes signs. So there is a point of inflection at x is equal to positive and negative 1 in this case. Okay, last but not least, we are going to try to do a short little sketch of this particular function using all three of these parts we just found. So again, we know, if we kind of zoom out here, we know that f is increasing on those intervals and decreasing on the other two. We know the minimums and the maximums. We also know the points of inflection and the concavity of the function itself. So we're going to try to give it a relatively accurate sketch, and then we'll compare it. I have one for us to look at. So we have the x and y axes here, and we know that some important values would be negative root 3 and root 3, which is, each of those is between negative 1 and 2 and 1 and 2. We also want the x-intercepts, or at least the one x-intercept would be 0, 0. All right, so we have a maximum here at x is 0. We have minimums. Oh, and by the way, when we think of our function here, and I'm sort of cheating this slightly by looking at it, but I know that there's a maximum at x is 0, and I know the function 0 at that value. So that's why I'm putting it at the origin. I mean, if we didn't have a sense of where it was on the y-axis, we would just kind of be able to sketch it, generically. For instance, the relative min and max, I'm not going to be too worried about where it is on the y-axis. All I know is that 0, 0 exists, and that is a relative maximum. I also know that the minimums are at negative root 3. I'm just going to say that's about here, and positive root 3. I'm just going to say that's about there. So I'm kind of ballparking the x value. I have no y-axis. I have no y scale on the y-axis, and so I'm not going to worry about that too much. We do know that the function is going to decrease from negative infinity down to root 3. So we know that we're going to kind of come down through the graph like this. And we also know, based on the concavity, that it's concave up there, which I know it's really steep, but that is concave up. And then it's going to kind of bounce off of this because that is a relative minimum. And the concavity is going to change at negative 1, which makes sense because this is a relative maximum and it's concave down through this region, and then the concavity changes at positive 1 again, and then it will increase forever. So it's going to go like that. So we're looking at the graph is decreasing to negative root 3, then it's going to increase, and it's going to change from concave up to concave down. Then it's going to be concave, concave down, and then it's going to change to concave up while it decreases, and then it will be concave up and then start to increase forever. So we're following each of the parts A, B, and C through that particular graph. Okay, I just imported just a picture from Desmos of the actual graph, so you can see that we have the behavior down, and that's what it actually looks like from the actual equation f of x. Okay, that is section 4.3. Thank you.